All right, let's talk about something that's moving from science fiction to front-page news: carbon capture. You've probably heard the term CCUS, carbon capture, utilization, and storage. Well, this isn't just a concept on a whiteboard anymore. It's a real, fast-moving field of technology. So today, we're going to trace that entire journey, all the way from brand new materials being cooked up in a lab to what it actually looks like when we try to deploy it in the real world, and what it costs. Ready? Let's dive in.
And this quote right here from Olivia Powys, it just nails the feeling in the industry right now. The whole conversation is shifted, you know? It's not just talk anymore. We've moved past ambition and are squarely in the action phase. We're talking about actual projects breaking ground, real money flowing in, and new jobs being created. This is the new reality, and it's the stage for everything we're about to break down.
Okay, before we go any further, let's get one key term straight. Carbon dioxide removal, or CDR. This is super important. It's not about slapping a filter on a smokestack. That's point source capture. No. CDR is about capturing CO2 that's already floating around in the atmosphere. Think of it like a giant vacuum for the sky. And when you do that, you create what are called negative emissions. It's a tool that's become absolutely essential in the climate playbook. Because let's face it, just cutting emissions isn't enough anymore. We need to start cleaning up what's already out there.
So, here's how we're going to break it all down. First, we'll set the stage with the big challenge. Then, we'll geek out on the new materials being invented. After that, we'll see how digital tools are speeding everything up. Then we'll get practical. How do we deploy this stuff, and what's the price tag? And finally, we'll look at what's next for CCUS.
All right, let's jump right into part one, the challenge itself. What's the problem we're actually trying to solve here? I mean, why is there this massive, urgent push for these technologies right now?
And here's the bottom line. We're just not cutting emissions fast enough. Not even close. The science is pretty clear. To avoid the worst-case scenarios, we have to get to net zero by mid-century. But we're falling behind. And that creates a huge risk of what's called an overshoot, where we blow past our climate targets for a while. So how do you fix that? Well, you can't just stop emitting. You have to actively go into reverse. You need years, maybe decades of net negative emissions to claw that CO2 back out of the sky. And that right there is why carbon dioxide removal went from being a kind of what-if idea to a must-have strategy.
Okay, so we've got the why down. Now for the really cool part, the how. If you need to capture carbon on a planetary scale, what do you even use? What's the tool for the job? Well, the answer is being cooked up in materials science labs right now. We're talking about scientists literally designing and building brand new materials from the ground up with one very specific job: to grab CO2 molecules right out of the air. And what's so fascinating is that there isn't one single answer. It's not about finding a single magic bullet material. It's about building a whole toolbox. You've got things like these graphene MOF composites, super complex structures that don't just capture CO2, they can actually help turn it into something useful. Then you have solid amine adsorbents, which are all about controlling the physical flow, like tiny sponges designed for maximum efficiency. You have materials like molten salt-promoted MgO, which are workhorses for high-temperature industrial jobs, and then something completely different, like tandem catalysts, which are designed to take CO2 and convert it directly into fuel. Each one is a totally unique pathway, a different tool for a different part of the problem. So you have this explosion of amazing new materials, right? But that creates a brand new problem. How in the world do you test all of them? How do you figure out which one is best for which job without spending the next 50 years in a lab just mixing and matching? Well, this is where things get really interesting, because the innovation journey takes a hard turn into the digital world. The answer is simulation and AI. Take a look at how scientists model a direct air capture plant. They have different tools for the job. You've got the local equilibrium model. Think of this as the quick and dirty sketch. It's computationally cheap, it runs fast, and it's great for getting a first look, especially in high-temperature scenarios where everything happens in a flash. But it cuts a few corners. Then you have the linear driving force model. This one is more like a detailed architectural blueprint. It's way more complex because it actually accounts for things like how long it takes a CO2 molecule to wiggle its way into the capture material. That makes it much more accurate for real-world conditions, but it also takes a ton more computing power. And this is a classic engineering trade-off you see everywhere: speed versus accuracy. And they have to make that choice every single day. And it's not just about simulating the physics. They're using AI to turbocharge the research process itself. I mean, think about the AI behind things like ChatGPT. Researchers are training these models to be expert assistants. You can do it two ways. You can fine-tune it, which is like sending the AI to grad school for a specific subject. You get incredible performance. That cosine similarity score is basically a measure of how well it understands the topic, and 0.94 is an A+, but it's a lot of work. The other way is prompt engineering, which is more about learning how to ask the AI the perfect question. It's faster, easier, and you still get really good B+ results. It's just a fantastic example of how even the tools for doing the research are being optimized to make everything go faster.
So, to wrap this part up, you can really think of these digital tools as the critical bridge that connects a discovery in a lab to a real-world technology. They let you see the future. You can simulate how a material will behave in a giant industrial plant before you've even made a kilogram of it. You can have an AI read and summarize 10,000 research papers in an afternoon. This just crushes the old R&D timeline. You can find the dead ends in weeks instead of years, and you can bet big on the winners all before you spend a single dollar building expensive prototypes.
All right, so we've got the wonder materials, we've got the digital blueprints. What's next? Well, we have to take it out of the computer and into the real world. And this is where the rubber really meets the road, where the science of what's possible crashes right into the hard realities of engineering and economics.
So, you've captured the CO2. Great. Now what do you do with it? You can't just leave it in a tank. You got to store it somewhere, permanently. And that's where geology enters the picture. Just look at this. This is the storage potential in just one region, Alberta, Canada, using old depleted gas fields. The numbers are just staggering. The Kirby-Lemming trend alone could hold over 770 million tons of CO2. Add up just these top three, and you're at almost 1.4 billion tons of storage capacity. The takeaway here is that in a lot of places, the storage part of the problem, it's actually solvable. The space is there.
But having all that potential space is one thing. How do you pick the perfect spot? Well, it's not random. It's a very deliberate step-by-step process, almost like a funnel. You start with a huge initial screening of thousands of sites. You're asking basic questions. Is it big enough? Is it porous enough to pump CO2 into? And the big one, is it sealed so it won't leak? Then you take the ones that pass and put them through a more rigorous ranking, looking at all the detailed geology. And finally, you bring in the money. You overlay the economic map on top of the geological one. How far is this site from the factory capturing the CO2? What would a pipeline cost? Suddenly, it's not just a rock formation anymore, it's a business decision.
And speaking of business decisions, that brings us to the elephant in the room. The cost. Always the cost. Let's look at two different designs for a direct air capture plant. One is a packed bed design, the other is a monolith design. They have different pros and cons from an engineering perspective. But look at the number that really matters, the cost per ton. We're talking about roughly 2,100 euros to capture 1 ton of CO2. Now, to put that into perspective, the price on a carbon market is often less than 100 euros. That is a massive gap. And this, right here, is the biggest hurdle. The tech is real, the storage is there, but bridging that economic chasm, that's the whole ballgame.
So that brings us to our final leg of the journey. We've seen the lab, the computer, and the price tag, so what's next? What are the big hurdles that everyone in this field is working like crazy to overcome right now to make this whole thing work at scale?
Well, here they are, the big five. First up, you've got material stability. These fancy sorbents need to be tough. They need to last for thousands and thousands of cycles without falling apart. Then there's kinetics, basically the speed. For some uses, the capture process is still just too slow. Third, the energy penalty. This one's huge. It takes a ton of energy to rip the CO2 back off the sorbent so you can store it. That energy costs money and has its own footprint. Getting that number down is a top priority. Fourth, the one we just talked about, economics, pure and simple. And finally, the sheer, mind-boggling scale of it all. To make a real dent, we need to build an industry the size of the global oil and gas sector, but running in reverse. It is a monumental challenge.
So, let's wrap this up. If there's one thing to take away, it's this. There is no magic bullet. The future here isn't about finding one secret material or one perfect design. It's about accelerating this entire journey we've just explored. Everything from inventing molecules in the lab, to simulating them on computers, to finding the best places to bury them, to engineering plants that don't break the bank. So the real question, the one that everyone is trying to answer, isn't what's the solution, it's how do we connect the lab to reality, and how do we do it a whole lot faster?